welcome everybody to the ABB TechTalks for Marine and Ports, where we focus on the grid to propeller, the strategy, and the shore connection. So thank you for joining. I hope that this next 60 minutes will be beneficial and useful for you. Before going to the actual presentation, a couple of housekeeping rules. If you keep your microphones muted throughout the whole session, we will also record the presentations and make the presentation then available to you afterwards. We have a 15-minute reservation for Q&A at the end of the session, and during the whole time you can put your questions in the chat box that you find on your screens, and you can type them there, and we will pick them up at the end. And the questions will not be visible to everybody, so don't get worried if you don't see them. Okay, quickly about the presenters today. My name is Markus Martelin. I work as a portfolio manager for electrical services, focusing on mainly on vessel side retrofits and modernizations, and lately also on the shore connection. Then we have two product managers. Luca Imperiali has an extensive background, roughly 10 years with shore connection, and acts as a global product manager for shore connection. And he's also a member of the IEC committee for shore connection. And then Jesse Makkonen has recently started in the position for a product manager for automatic chargers and cable management systems. And this is I would say very recently established position as we see this field very essential when we talk about shore connection. And then we move on to the actual agenda for today. So I will make a very brief introduction to the topic, and then Luca and Jesse will continue with the shore connection, starting from the land side and moving to cable management and then to the ship side, and at the end of the presentation we have the Q&A as mentioned. So as an introduction, we can take a quick look at the market drivers when we talk about shore connection. We see that regulation, whether they are global ones or country specific or even ports specific, has an increasing effect on the development of the shore connection. Emissions, whether they are global or local, it has an impact, and it is also driving this market. Also, I think it's fair to say that also green profiling and the brand issues for ship operators and the ports is essential, as well as the passenger comfort on certain ship types, and then the reduction in the OPEX. Of course, this can be varying quite a lot case by case, that is the OPEX saving really in place. But this is to summarize the main drivers in the market. Then, like let's say additional drivers, when we talk about automatic connection systems and the hybridization of ships in general. Often when we have a battery system on board the vessel, the battery plays, of course, a very essential role in the whole system, and then the charging time of the battery becomes very relevant. And of course, primary needs for the ship operator is to maintain the existing operation schedules and not to modify them too much. There is a need to not to add labor to the cable handling if it can be done in an automated manner. And of course, if we save time in establishing the connection, we are maybe able to also reduce the capacity of the battery, which then has a direct CapEx impact, and we can really optimize the battery system to fit the operation profile. So then finally, we come to what we mean by the grid to propeller. We mean the whole powertrain from the shoreside substation to the cable management and all the way to the vessel. And here I want to highlight that ABB's role is really to be in the system integration and not act as a component deliverer. We have an extensive background on the shipside installations, and now we utilize that knowledge and competence also to establish the connection from the land side. So with this introduction, I would hand it over to Luca, who starts to talk about the land side shore connection. Luca, yep, please.
Yes. Hello, and welcome to this introduction to shore connection. One of the main challenges of shore connection is definitely the interoperability. That means the possibility for a vessel built in US, for example, to connect to a facility here in Europe or in Asia. This has been always one of the biggest challenges for this application. And for this reason, some time ago, ESC, ISO, and IEEE joined forces and created a joint working group, the Joint Working Group 28, that had the scope of building a consistent set standard that assure the interoperability between vessel and ship built in different places in different countries, following different rules and in some cases also different technical standards. Up to now, these standards, this standardization committee have built three main standards for what we call the traditional shore connection, also known as AC shore connection, the standard for the high voltage shore connection, the ESC IEEE 80005-1, the standard for the low voltage shore connection, the 80005-3, of which is now available a PAS, that is a public draft available for public comment. And the main standard is currently under development. And a further standard, the 80005-2, that is a standard designing the data communication between ship and shore. That is in some way proposing a further advanced, smarter shore connection, meaning a shore connection where the ship and the shore speak together and achieve a higher degree of automatization. There is also a further development, work in progress at the moment, that is mainly focused on DC vessel, but also on DC shore connection. This further ESC 63108 is a standard that defines not only the design of DC vessel, but also how to establish the shore connection for this sort of vessel. And we will see further on how important it is for a DC vessel use of shore connection. In traditional shore connection, we can identify mainly three parts. We can split the application in three parts. One is the onboard part, that is mainly the interface and the control system on board the vessel, because at the end is the vessel that is in full control, also do all the shore connection before and after the connection with the shore. The cable management system, and this system change a little bit case by case. In some cases is on shore, in some cases is on board, depending on the type of vessel. And the infrastructure on shore, that is mainly substation, with or without frequency conversion, depending if also the frequency need to be adjusted between the ship and the shore, and the distribution to the vessel. The traditional standard, the traditional shore connection, identify different type of characteristic of the shore connection depending on the type of vessel, because different vessels have mainly different requirements in terms of power. So we can go from a shore connection for a cruise vessel that is quite demanding in terms of power, and here we can see a different type of solution, one for one single vessel. So one large frequency converter capable of delivering up to 16 MVA, that is considered to be a little bit the minimum necessary for a cruise vessel, with a different connection point on the berth, because there is no standard position of the connection panel on board the vessel. And on the right side, we see something different. It's a centralized frequency conversion that is capable of delivering power up to two large vessels, each one with its her own galvanic insulation on shore, for a total power of 20 MVA for each vessel. Moving from the cruise vessel, that is probably the most demanding application in terms of power, shore connection, we can go to the container vessel. Nowadays, there are hundreds of container vessels using daily shore connection in Los Angeles, Long Beach, now also in Auckland and Vancouver. This shore connection is for some way similar to the one for the cruise, because there are more connection points for the same vessel on the berth. But here the power required for the vessel is is definitely lower. Here we are talking about a theoretical value of 7.5 MVA for vessel. But we know that the real consumption nowadays is definitely lower than this. So there is space for optimization. So we can think to have one centralized frequency converter that feed more vessels at the same time. Usually it is a common use to dimension each one of the galvanic insulation on shore for the 7.5 MVA, while sometimes we can optimize the use of the frequency converter. So for example, with 15 MVA frequency converter, we can feed 2 or more vessels, because the real consumption is definitely lower than the one from the standard. It is also possible to eventually increase the size of the frequency converter in a second time. An additional solution, additional type of vessel that have successfully used shore connection since a very long time, especially in the north of Europe, in the Baltic Sea, in Sweden, but also in other countries, is a shore connection for ro-ro ferries. This particular type of vessel have the characteristic of being, for the main part, low voltage vessel. So the moment you want to connect this vessel in high voltage, and this is the easiest way to achieve a very fast connection, because a vessel can be basically under shore connection in 5 minutes. Since all these vessels have galvanic, already a transformer on board, and this transformer is already providing galvanic insulation, it's basically possible for this category of vessel to connect to the same bus bar. So in the picture here, we can see a centralized conversion that can deliver for the same vessel docking on the left side here on this bus bar at 11 kilovolt, both 11 and both 50 and 60 hertz. In this case, the vessel, since the grid is already 11 kilovolt, the vessel will connect directly to the port grid. Another characteristic of this sort of vessel is that they connect daily. So this topology is also achieving a sort of heavy-duty operation. So it operates each function, that is the connection to the 50 or to the 60 hertz and the grounding of the short connection for safety reason when it's not in operation, is achieved through a dedicated device, a dedicated earthing and disconnector switch. And finally, there is the low voltage short connection, what is in the ESC IEEE world is called by 80005-3. That basically is a connection usually reserved for vessels that have a consumption around 1 MVA. So there have been identified 4 standard values for this short connection. So the 400 volt, the 440, and the 690. There is a little bit of flexibility for the power that you can deliver to the vessel, because of course 600 and 690 can deliver a little bit more power respect to the 400 volt. This concept is a little bit different from the concept of the high voltage short connection, because in high voltage short connection, different type of vessel will have a different type of interface. So for example, a cruise have 4 plugs, Ro-Ro and ferries has 2 plugs, 6.6 kilovolt, container vessel have 2 plugs at 6.6 kilovolt. Ro-Ro and ferries has 1 plug at 11 kilovolt. In low voltage short connection, the decision is to have a different and more flexible solution. So whatever is the type of vessel, they will connect, will find on shore a facility, a flexible facility with 1 or more plugs, up to 5 plugs, and that is able to deliver up to these 3 standard voltages, the 400, 440, and 690 volt, and the 2 different frequencies, the 50 and the 60 hertz. The vessel will connect only with the number of plugs that it actually requires. So this is a system, let's say a solution, a design that has been developed to limit the retrofit necessary on board the vessel. That is basically and simply a panel on board. And this solution is very suitable to be also containerized. So the solution for this sort of application can really limit to the minimum the works to be done on the portual infrastructure for the connection. And finally, there is this DC short connection. DC short connection is something that quite new, the market. The most recent case dates back a couple of years. It's a different concept respect to the traditional short connection, because in traditional short connection, basically what you want to achieve is basically that the vessel shut down the engine when it's at berth. So you are providing basically the power that usually the vessel would generate on board. So they can shut down the engine. That's simply the real scope of traditional short connection. In DC short connection, you are basically feeding a hybrid or a DC vessel that rely on batteries as main source of power, also during navigation. So this short connection is not only necessary to allow the vessel to shut down the engine when it's at berth, because basically in some cases there are no primary engine on board. The only source of power are batteries. So what you need, the scope of the shore connection is basically to recharge the vessel, as for e-vehicles. And for this reason, the solution on shore is a little bit more sophisticated. It relies not only on transformer and frequency converter, but also on DC link and DC-DC converter, and batteries in case the power source on shore doesn't have enough available power to cover the high demand of energy of the vessel during the recharging. So in this specific case, it is most probably also necessary to share information between the ship and the shore. So data communication in this case, it becomes fundamental for the, let's say, correct operation of this sort of connection. And this is, on our point of view, probably the future of the most promising and interesting development of this sort of market. Our proposal is to drive our customer from the beginning, so from understanding which are their needs, which are their requirements and limitations, up to the starting of the project, so the choosing which are the best, which is the best solution, and through the project execution, so building actually the infrastructure on shore, but also retrofitting the vessel, or even building a brand new vessel, and I mean, keeping a strict relationship with our customer down with the service, maintenance, and eventually for the development of the solution. I think it's now time to move to the part of the cable management system and the automatic chargers. So I leave to Jesse.
Thank you, Luca, and also good day also from my side. So it's Jesse Makkonen speaking. And welcome to have like a quick sneak peek about the connection devices. Yes, as Luca mentioned before, it is really interesting or important to understand that there are two different kind of market segments. We have the shore connection, and then we have the shore charging. In the shore connection, as Luca mentioned, the vessels are connected to the shore supply, and the engines will be turned off. And then in the shore charging, the batteries are charged. And the easiest way to start explaining what the different connection methods are is to use the specific chart here. And there the x-axis is meaning the connection time. And the shorter the connection time is, then more automatic devices are needed. And the longer it is, and then the connection time is not so critical, so then there is a possibility to use some manual connection devices. With manual connection devices, the connection time is normally from 5 minutes to some hours, depending the scope and the type of the device. But then with automatic connection devices, it is possible to achieve like a connection time from 10 seconds to up to 1 minute or something like that. And then the y-axis is describing the available power. So it means that the more powerful charging need bigger toys. And in the charts, the low power vessels are described to use these EV things, and then the more powerful devices are the robot charging, and then the mobile cable management system for cruise vessels. Then there is also possible to divide the charging to two different kind of methods. There is the short-term fast charging, also meaning opportunity charging, and it means that the vessel is sailing between fixed route, and the batteries will be charged during the normal operation. So it means that the layoff times are very short ones, and the batteries are charged during the short layoff time. Then the second option is so-called destination or layoff charging, which means that the vessel is staying in the harbor longer time, normally, for example, during the night time, and during the night time the batteries will be charged fully, and then in the morning the batteries are fully charged and the vessel can start the daily operation. Then if we start from the manual connection devices, and these so-called cable management system can be used for charging or shore connection, and there are AC and DC systems available. The IC systems, as Luca mentioned before, are standardized by IAC committee, and so the systems are following like strict standardization. But then the DC solutions are still under development. The IAC standard is defining as product segments that what kind of cable management system is needed. For example, it is possible to divide those to three different kind of. For example, the dispenser one, meaning the fixed cable management systems, and those are mainly meant for ferries, ro-box ferries, and ro-ro vessels. Then there is the mobile cable management system, which is mainly meant for cruise vessels, meaning that the different kind of cruise vessels are arriving to the harbor, and the connection point is not fixed, so it is needed to change the connection point in the dock side. And then there is the third one, which is the container cable management system, which is, as the subject is telling, is meant for the container vessels, and there the plugs are locating on board. What is the difference between these different segments is that the voltage range varies a lot. For example, the fixed cable management system and the mobile cable management systems are defined by the IAC standard that the voltage range is from 6.6 or 11 kV. But then in container cable management system, the voltage range is fixed to 6.6. The power range is also different. So with this fixed cable management system, it is possible to go up to 6.5 MVA. With this mobile cable management system, you can go up to 20 MVA. And then in the container cable management system, it is possible to, or the power is limited to the 7.5 MVA. Also, the tidal variations are handled differently with these different kind of products groups. For example, the dispensers, the tide is compensated with the length of the free cable, which is hanging from the dispenser. And then in the mobile cable management system, you can adjust the connection point to match with the tide, changing the position of the boom. And then in the container cable management system, the tidal compensations are handled with the length of the cables. And there it is possible to have cables up to 60 meters. Then if we go to the automatic connection devices side, there are also three different kind of segments, and the most common ones are the bow charging and the side charging, and then there is the new area, which is the top charging in the future. In the bow charging means that the charger is locating in the shore side, and it can be off-ramp or on-ramp installation, depending the ramp structure and the need of the client. And if we are comparing that to the side charging, then like a side jetty is needed for the installation, and the connection is happening from the side of the vessel. There is also like differences between these two different kind of connection methods. For example, the bow charger, normally they don't need like additional mooring, but then with side charging, the additional mooring device is highly recommended. Of course, the additional mooring will increase the total cost and increase the complexity of the system, but there is of course pros and cons. And then with bow charging, there is no like a mechanical interlock with the vessel, so it means that the quick emergency release is not causing any mechanical challenges or failures, and it can happen very, very fast. So even when the connection point is in the bow, then it means that the vessel can even leave from the berth with the plug connected, and that is not causing any harm. And if we are comparing to the side charging devices, when the connection point is in the site, then there is like a physical interlock with the vessel, and then the emergency disconnection takes a little bit longer because you need to pull out the plug before you can like leave from the berth. Yes. And then there is the third option, which is totally new in the market, so-called like top charging, and it is normally meant for smaller passenger ferries, where the charging power is approximately 1 megawatt. But there is a lot of opportunities in the market, and that is the way where we really want to aim. And also one thing is that what is ABB's role with this cable management system and shore connection and shore charging market is that we, as Markus mentioned, that we want to be like system integrators, meaning that we don't have own products, and our goal is to integrate the charger or the cable management system to our overall system, and of course guarantee that the technologies that we are supporting and proposing are fully working and reliable, and it is fully integrated to the system. So then the customer is gaining more than the black box to the shore. Yes, but I think that was everything from my side. If you have any additional questions or everything, please don't hesitate to contact me, and I will hand over back to Luca. Thank you.
Up to me again. We will move now through the onboard part of the shore connection, and we will start again with what is the traditional shore connection, again what is covered by the ESC IEEE standard. In traditional AC vessel, the main distribution is done in alternated current. Voltage can be high or low voltage. Usually, and standard voltages for distribution on board are 400 volt for 50 Hertz vessel, 440 60 Hertz, 690. It's a common voltage for 60 and 50 Hertz vessel. Bigger vessel as main part or totality of a cruise vessel, but also as some container vessel, have basically a distribution in high voltage, that in our case means medium voltage, that usually is 6.6 or 11 kilovolt. The main distribution, as we said, is in high voltage, and the power electronics in this case is limited to optimize the propulsion. So, for example, in case of Azipod, the power electronics is driving this special propulsion system that increases the system efficiency and the flexibility of the vessel. But it's limited to this, we can say. Shore connection here is used mainly to allow the vessel to shut down their engine when they are at berth. So no other no other things are performed by the shore connection. So it's a dimension usually only to cover the hoteling and what is the vessel is requiring during the usually short stay at berth. In hybrid vessel, the configuration starts to be a little bit more complex. So it coexists the presence of AC distribution, that is the main part of the distribution on board, for example, to the auxiliary service and in some cases also to the from the traditional engine. And this coexists with integration with some energy storage that allows the traditional engine to run at the maximum efficiency. On this point of view, an hybrid vessel is very similar to an hybrid land vehicles. The shore connection here plays a little bit a different role. The shore connection is usually in AC, so it's following the normal, the traditional standard of ESC IEEE shore connection, but is used to recharge the batteries during the stay at berth. The batteries are not the only source of power in this case. They are integrated with a traditional generation, still to increase the autonomy of the electrical autonomy of the vessel. During the stay at berth, the shore connection is used to recharge the batteries. This poses some challenge also for this hybrid vessel, because the amount of power that can be required to the grid can be higher. So on shore, it is possible to integrate also with some energy storage to limit the amount of power that is required from the grid. And also the shore connection itself, if following the standard ESC rules, can be not enough to deliver the whole power. So, for example, in this picture is shown a vessel that can connect to both sides. This could be strange if you think to a traditional large vessel as a cruise vessel, but if you think to a very small vessel that is docking on a special berth, there is the possibility to connect on both sides. And we move now to what is the most innovative development, a vessel that have mainly electrical propulsion on board. So the whole distribution is can be in DC. AC can be limited only to some auxiliary power for some traditional consumers on board. The shore connection here is definitely more demanding, and in many cases, the stay at berth is use of traditional shore connection is incompatible, as Jesse was saying, with the short time at berth and the amount of power that you need to deliver to the vessel to charge, to completely charge the battery pack. So in this case, innovative and fully automatic charging system are required, so systems that connect in very fast time and also exceed the capability of the traditional shore connection connectors, so above the traditional 350 or 500 amps. Another characteristic of the system is that since it's connected in DC, so a DC vessel connected to a DC facility on shore, can be designed in a way that there is a full control of the ship over the shore. So on shore, there could be batteries in a way that the the impact on the existing grid is extremely limited. So basically the grid onshore charge the onshore batteries, I don't know, during the period where the battery is not there, and then discharge the onshore batteries into the onboard batteries during the short time presence of burst. In order to do this, there is a strict coordination between the charging system or the battery management system onshore and the control system on board. So this is the case where we can really start to talk about full control of the vessel over the shore. This is one of the segments that we think is probably more interesting for the future. A system that we think will be, let's say, will drive to a more compatible future of the navigation respect to the environmental impact. And I think that we can move now to the section of question and answer. Thank you for participating to this webinar.
Okay, thank you, Luca. I think we are pretty well on the schedule. We can move on to the questions and answers. Please type in the chat box if you have any questions. We have a few here. We can take them. I just changed the slide as the last slide. I will take the first question. Does ABB only supply systems with ABB produced connections, or do you consider systems from other manufacturers as well? I can answer to that and say that we do use also other makers' products in our system. So of course certain key components like let's say frequency converters or PLCs, they most likely will be ABB make, but we take them case by case if we see other vendors' products which are suitable and reliable in the system scope. And then there was also a question coming about the future development of the IEC standard. I think, Luca, you would be the best one to answer to that.
Yes, here, ready. Which is the future development of the standard? I think that one development is definitely in the direction of integrating in the DC into the so developing a dedicated standard for the DC shore connection, and for the development it's also required to integrate this automatic charging system. So the whole concept of the current standard in shore connection is in some way including some manual operation of the plug. There are a lot of requirements, necessary requirements for the safety of the personnel handling the plug. But this means that the moment that we remove this manual handling, so the moment that we robotize or automatize the whole shore connection, it should be possible to integrate the safety into this automatic philosophy. This is definitely a further development of the standard. So I will see on one side the development of the shore connection in the DC shore connection. On the other side, the development of automatic shore connection, so a dedicated standard or a new annex of the standard for this. And finally, what we see with some interest is also the possibility to use or integrate what has been developed up to now for small vessel EV charger for vehicles. There is still some development to be done because the current EV charger plugs and sockets are not suitable for marine environmental, but there are several development projects that are going into this direction. So that I would say that there are these main three development. So integration for small vessel, possibility to use the same interface of EV charger. For DC vessel, a dedicated standard, and for the development they take into consideration this fully automatic connection.
Okay, thank you, Luca. I think we then move on. There is a question from somebody asking that what are the technical limitations to go for bigger vessels with DC grid connection? And there's quite a similar question about that it was mentioned 5 megawatt charging power. Is that correct? So I think the same answer might go to both of these. So maybe Jesse, you could take this one.
Yes, I can try to explain. So thank you for the question. And from the charging point of view, the charging power is of course limiting the DC grid solution. And nowadays there is a discussion. First of all, the limiting factor there is the charger normally. And nowadays there has been discussions ongoing with the suppliers that the new maximum charging power with DC is somewhere there between 7 and 8 megawatts. But then in AC it is possible to go up to almost 10, 13 megawatts. But that is correct that there are like limiting factors with DC chargers. But yeah. Hopefully that will answer the question.
Okay, thank you. Yes. And there's a question about how do you see the yearly market potential for shore-to-ship connection projects in Europe? I'm not able to give any, let's say, numbers on that. There are many studies and research has been done on the market potential which are available. Apparently they are very, I would say, huge numbers globally. And if I remember the kind of the projection for the next coming 5 years, it's basically saying that Asia is the fastest growing market when it comes to shore connection, and Europe is the kind of most established one. So presently the market is biggest in Europe, but the growth is not so fast in the next coming 5 years. I would say that the activity in Europe is there's a lot of activity in the market at the moment, both with the ship owners and on the terminals. So there's a lot of activity there, but I'm not able to say any let's say figures. Okay. Then we had the question still about the EV chargers used in vessel charging. I think, yes, so you have spent some time with the EV. Would you comment on that?
Yes, of course. So we have also noticed that the market potential in the EV business is huge, and it would be a clever idea to use the existing technology in marine. And what we now have found out is that the existing EV technology for vehicles is not suitable for marine environment. There are a lot of challenges with the IP rates of the equipment and the cable lengths and how in EV vehicle world the interlocks are happening. But there is a huge market potential, and hopefully during the next year it is possible to solve those issues and go on live to the markets. And the preliminary discussions are now that the chargers, the manual charging can go up to 500 kilowatts, and then for the automatic connection devices, it is possible to provide 1 megawatt hour charging power. So the market is there, and we need to aim there also. Thank you.
Thanks, Jesse. I think we are now done with the questions. At least I don't see any new ones coming in. So I think we are okay. There's one more just popped in. Question to LV shore connection. How do you manage corrosion caused by the shore connection? Is an insulating transformer required on the vessel? I think, Luca, this one goes to you.
Yes, I think. Well, I mean, the biggest challenge is not really the corrosion is definitely a big question, a challenge. Not for the shore connection itself, not because the power system is connected, but because one of the main ways of avoiding electrocution is to connect together all the metallic parts of the ship and of the shore. And of the shore means to ground, basically, to the land ground, the hull of the vessel. And this is creating a path that includes metals with different capabilities. So there is a natural corrosion here, but this is not related to the shore connection itself. It's not because the main power system are connected. So basically, one way of reducing or eliminating this aspect is there are available on the market some system to avoid corrosion, some passive methods with sacrificial anodes, or with some active system that basically avoid that is the hull of the vessel to be corroded. But these have limited relation with the fact of galvanic or not insulation, because what is present in small craft, that is the possibility to completely disconnect galvanic insulation in the small craft means that you are also disconnecting the two earthing system. You are really disconnecting them. But in inshore connection, the hull is always connected to the ground. There is no way out of this for safety reason. But there are systems to reduce the corrosion. That's more or less the question to this. There is, of course, a bigger challenge in the seashore connection, because in the seashore connection, there could be an overlap of the power path to the main corrosion. For this reason, we usually propose solution where the DC, also the DC on shore, is galvanically insulated from the rest of the grid. In this way, we are avoiding to overlap the DC with the DC shore connection with the earth path.
Thank you, Luca. Now I think that was the last question, or at least there hasn't been any new ones coming in, and we are slowly reaching the end of the time slot that we had. And of course, I mean, if any questions come up later, then please contact us. I suppose you will find our information for the email, etc. So you can contact us also later. And the recording of this session will be also made available to you, so you can then share it with your colleagues if you see that beneficial. So with these words, I'd like to thank you for the participation, and I hope it was useful, and I wish you a very enjoyable rest of the day. Thank you. Bye-bye.